Okay, and welcome back to Supernova Labs. So today I wanted to talk about something that was maybe a little bit different from the things I've spoken about so far. So I've spoken about cryptocurrency, I've spoken about space, I've spoken about decentralized networks of labs. But maybe we wanted to go into something a little bit more fun, something that I'm passionate about, and isn't going to have like major success anytime soon. So for a long time I've been looking into fusion reactors and how they're working, like why specific ways of building fusion reactors aren't working right now. And I just wanted to go over some of the stuff that I found because I find it interesting. Maybe you'll find it interesting too. So there's a consensus in industry right now around a certain type of reactor called a Tokamak, and these are reactors that are primarily donut shaped. So you have like rings of magnets going all the way around a like donut shaped chamber, and the plasma circulates inside of these rings of magnets, getting faster and faster and faster and faster and faster and faster and faster, like it's basically a big particle accelerator, until they are at millions of times the temperature of the sun. And at that point they bump into each other so fast that sometimes they fuse and release a lot of energy as a part of that, and that is the promise of fusion reactors as a means of producing energy. Now there is an element of efficiency to that hasn't been breached yet, or maybe it's been breached once. Let me check that before but a lot of the time it costs a lot more energy to get all of those particles spinning up in the right conditions, like contained within these massive superconducting, super cold magnets, just to get a small amount of energy out. And there is a term in the industry called Overunity. So there's like this thing called Q value. It's used in sound and speakers, as well as in like a whole bunch of other things. Basically measure the efficiency. It's basically the amount of energy out versus the amount of energy in. And if it's less than 1, it's costing you energy. If it's more than 1, you're gaining energy from it. And the goal is to get an Overunity reactor, so you're getting more energy out than you're putting into it. At that point you can connect it up to the grid and serve the general public. However, looking at fusion reactors and like the industry and the attitude within industry, there is this meme that keeps going around, is that fusion reactors are perennially 30 to 50 years away, or commercially viable ones, which is a self-limiting belief. And it also speaks to the current state of the industry, in that there's a lot of inertia surrounding tokamaks. Like, I think about the size of like a lot of the large reactors like ITER, like East, where there is these huge investments going in, like massive chains, like supply chains that go along with it. It's very difficult to tack in a different direction. Now, what I hope to lay out today is how these reactors are maybe doomed to failure. I think maybe if you put enough energy in, you will eventually get some useful energy out, but I think that it's always going to be quite inefficient in the way they're built. Because if you look in nature, you don't see donuts. You don't see donut-shaped fusion reactors. And there's a lot of tricks that you can do with these tokamaks. Like, you can warp the field so the plasma is like flipping over itself and going faster in certain areas, and doing loops and backflips and all this kind of stuff. Very expensive, but the fundamental problem with these reactors is that there is no center. And it's at the center of stars that fusion happens. So if we're not trying to model nature in the way we're building these reactors, I think we're always going to be fighting an uphill battle in terms of getting any useful energy output from them. Now, there are other designs for nuclear reactors. There's inertial confinement with lasers, basically like pointing a lot of lasers at something and just like firing a load of energy at it, which is maybe better long term. I think there's maybe some adjustments to the way I would do it if I were doing it. Or just like massive compression events, so like pulsing pressure into a chamber to try and force everything together. And I think that speaks to the fundamental issue here, is that one, you have issues surrounding geometry and the way that these reactors are built. On the other side, you have the way that you're trying to get these particles to fuse, and a lot of them seem to be, how do we force this together as fast as possible and then like compress it down to the point that fusion is just going to happen. And if I learned anything from condensed matter physics when I was at university, it's that you need to set up the conditions for physics to take over. And I think this is probably a better time to flip over to like, well, what do we see in nature, right? So if we look at stars, we look at pulsars, we look at yeah, I think we can just stick with those two. You have these spherical objects in space that are spinning on an axis, that have jets of high energy radiation coming out of the poles of it, and structures that form in a plane that is in line with that direction of rotation. Now, there's a guy, I mean, he's a bit controversial, I will admit. I'm not saying this guy is like the be all and end all of it, from Primer Fields, who has taken what's called a double torus. So if you imagine two donuts squashed together but with a center point, that's the design of the field that you need. And when you compare that to the donut shaped tokamaks, it's basically an inversion of that. So the space that they use to contain the plasma, they use to produce the field. So it's actually the space in between that produces this center point, but also an engineered magnetic field around which you can have your plasma circulating, but it always comes back to the center. Now, double torus, if you imagine particles going around like this, they'd be going around like this, but also like this. So you end up with like compression in that center point there, and a radial escape around the center. And he's had some success with it. I mean, I've seen one video where he has these shaped magnets. They look like bowls with a hole in the middle, and plasma moving around it, and it seems to be moving in the right way. But I think the problem is with his magnets are they're proprietary, so it's very difficult to get an idea of, well, how do these actually work. He's very secretive about it. He's going to be one of these guys where he ends up taking his work to the grave. I'm almost certain of it, and we're going to have to redevelop the whole thing again. That being said, I wonder if there's a more simple way of doing it again, because I guess my intuition surrounding it is that you have this radial mass of particles that come together in a way where they almost key together, and at that point there's a fusion event, and there are, I don't know whether, because like whenever in physics there's a, you'll hear a lot sometimes about 511 keV photons and why people look for them, because when you get antimatter and matter colliding, it produces two photons that move apart in exactly opposite directions. So that's the way they do some medical imaging, for example. It's where you can actually look for these bursts of photons in space as well, to detect certain astronomical bodies. And I think it's really interesting that you have this kind of like polar ejection of photons from stars and from pulsars and all this kind of thing. So it speaks to something like that going on in the middle. Now, this gets into some more esoteric stuff now. When you look into sacred geometry, and you'll see like the flower of life before and all that kind of thing. This is actually a two-dimensional representation of a 3D object. So Buckminster Fuller, in his work, managed to work out this vector equilibrium of, if you imagine you have a center point and 12 vectors that come off the center, it forms a specific shape, and all of those vectors are equally spaced, so they are in equilibrium. Now that's interesting, particularly because a lot of chemistry is based around carbon-12, and carbon-12 is one of the most stable elements. And you can expand out that structure, and there's a lad called Nassim Haramein who has like kind of like intuited this, what is it? What did he call it? It's like an extended vector equilibrium that goes at like an order of magnitude larger than what Buckminster Fuller designed in the first place. And what's interesting about that is it kind of speaks to this like kind of fractally collapsing structure that you can get. Buckminster Fuller talked about the jitterbug movement. So there's these 12 vectors can kind of like wobble together, and it creates compression and expansion within the system, but along trajectories, right? So this is where this all kind of comes together when I'm talking about things keying together, is that if you can emulate a system where you create pathways or low energy pathways for particles within some vacuum chamber to travel along inside a magnetic field, such that if they follow those paths they key together, you may end up with, well, this is it, that you may, my intuition is you'll be able to get a much lower threshold activation energy for fusion reactions. So I don't want to like go talking about cold fusion or anything like that, because I think there's a lot of BS that's polluted the water with that. But I think just a lot of what I haven't seen in the industry is enough of a analytical geometry approach to like how do atoms come together and how do they mesh, because I think a lot of people still work from this whole like ball and stick model of atoms and like neutrons and protons being like stuck together in an atom and like The reality is that it's probably nothing like that. And if you imagine like scattering angles for particles, right? These correspond to actual angles that you can approach something at. I think there's a huge problem in particle physics at the minute where they have all these terms for defining properties of atoms like quantum numbers and scattering angles without realizing that actually, I mean, like we call them spin. And there's almost like an intuition towards that. Now, you can go a step further with this, like with all the quantum numbers. If you look at the eightfold way for cataloguing all of the different particles that come out of the various particle accelerators, like linear and circular, like CERN, for example, and they form this this hyperdimensional geometric structure, and each of the particles form a node on that structure. So my question becomes, well, is there a way of approaching the geometry in physical space? But then also, is there a way of approaching this in hyperdimensional space as well, so that you get these, like, I used an analogy the other day, and you can kind of get lost like talking on all these like large terms. It's like the difference is the state of the current fusion industry is like, well, how do you force a square peg into a round hole, versus the approach I'm advocating for, which is almost like, how do you invite these particles to dance? If you create the right conditions for them to come together, they will come together. And with that, I think that's probably a good note to end on. I hope you have a wonderful day, and I hope we will be able to bottle Starlight soon.